Now, exponential growth, we actually have already done last class. We did exponential growth finance problems. So this is kind of a continuation of last class where we're getting a little bit more broad. There are other types of exponential growth that we can deal with, and also we're going to go over exponential decay as well. Now, last class, remember, we had this formula for finding amounts, total amounts. We had our principal, which was our initial amount. So this was last class. Then we multiplied that by 1 plus the rate over the number of times you're compounding per year, or raised to the power of the number of times you're compounding per year, times time. This class, or right now, we're going to look at exponential growth for finance and also other problems when you're only compounding once per year. It's only a yearly thing. When you're only compounding once per year, the n value in this function, in this equation, the n value is 1. So the n disappears, right? It's invisible. So when we're just compounding once a year, we have this formula. Now, instead of writing P, I'm going to write an A. I'm going to write a little a, just so that you're aware that this also applies to other problems besides money. Peyton, that might be because it was decreasing. So you have to look, so you have to look at whether or not your, you have to look at whether or not it says it's declining. We actually are going to come across a problem here in a couple of minutes where the interest or the amount is on the decline. And if it's on the decline, then you have to put a negative in front. But we'll get to that. So anyway, I'm replacing that P with an A. The A is still the initial amount times 1 plus, now remember the N is now 1, so we just have an R, raised to the power of T. This is when we are just compounding once per year. Yearly. And then the only difference when we're compounding just once per year, the only difference for decay is that instead of adding 1 plus R, we subtract. Okay. So now this is very similar to what we did last class. So I'm not going to do all of these problems, but let's at least do, I think, the first and the last one. So here it says Brooke started her career with an annual salary of $32,000. Each year thereafter, her salary increased by 2.5%. Write and use an exponential growth function to find her salary when she retires after 30 years. So this wants us to do two things. It wants us to write the formula, the function, and it also wants to figure out what her salary will be after 30 years. So first let's write the formula. We have, now it wants a exponential growth function, so I'm going to write this in function notation. F of t is equal to our initial amount, which is $32,000, that's her starting salary, times 1 plus, now because we're increasing, I do a plus. What is my rate? What rate do I write down here? Yes, guys. It is 0.025 because we take the decimal place and we move it 2 to the left. Or you can think of it as dividing by 100. To the power of t. So now that we have our function for her salary, we can now figure out how much her salary will be after 30 years. Who knows what her salary, or not what her salary, but who knows how we could find how much her salary is after 30 years. What could we do to figure out how much her salary will be after 30 years? Yes, Peyton, exactly. You just substitute 30 in for T. So instead of writing a T, I'll have a 30. And I just added those, whoops, I should do rate. That doesn't look like a exponent, does it? Raise to the power of 30. And then I just take this and I plug it into my calculator. So I have 32,000 times 1.025 raised to the power of 30. And you get 67,122.16. That's what she'll retire at, which is not too bad. It's actually a decent amount. All right, any questions on this first one? Also considering like retiring in 30 years is not really realistic. Because think, you start working at 20, in 30 years you'd be 50. People don't retire at 50. Unless you're like a cop. They retire pretty early. Or in the military, they retire early. Okay, sorry. Side tangent there. Let's do number 3. I'm going to skip number 2 because it's pretty darn similar to number 1. And let's do number 3. Kate drank an energy beverage with 150 milligrams of caffeine. Each hour, the amount of caffeine in her system decreases by about 12%. Write and use an exponential decay function to find the amount of caffeine in her system after 8 hours. So I'm going to write the function first. Now, because it says this is decreasing, what type of problem is this? Yes, it's a decay, meaning I'm going to write down my initial amount, which is 150. But then when I write my 1 and my rate, I'm going to subtract them. And my rate is 0.12 raised to the power of t. So now I'm trying to figure out, okay, how much of this caffeine is in her system after 8 hours. So just like I did in number 1, I'm going to take, yes, exactly. I'm going to take that 8 hours and I'm going to substitute it in for t. Wonderful, Lauren. Okay, so instead of writing t, now this is 0.88, 1 minus 0.12 is 0.88, and instead of writing t, I'm going to write 8. So I have 150 times 0.88 raised to 8. Meaning she will have 53.95 milligrams in her system after 8 hours. I don't think that's realistic. Maybe it is. Thank you. All right. Any questions about a decay function? Okay, so now one more decay, but this is a special decay function because it says the words half-life. Anytime your problem is referring to a half-life, you're going to use a special decay function. Instead of using the one that we used up above, half-life has a special function that we use that has the initial amount still, but here, you know what, it's still 1 minus our rate. And our rate for a half-life is always a half. So 1 minus a half is a half. So this number is always going to be 1/2 every time it refers to half-life. Also, the t that is in the exponent, we divide by the half-life. T means time. H is how long it takes for the substance to decay by half. That's what a half-life is. So here it's referring to the half-life of mercury 197 is 3 days. That means in 3 days, mercury 197 is 50% gone. It has decayed by 50%, by half. Okay, so let's try to apply it. The half-life of mercury 197 is 3 days. Write and use an exponential decay function to find the amount of mercury 197 left from a 50-gram sample after 20 days. All right, so let's start writing our function. Our initial amount here is 50 grams. It's a half-life, so I put my base as a half, raised to the power of time, divided by the half-life. Now, what is the half-life? What's my half-life here in this problem? Should I start calling people? Let's see. Let's do somebody I didn't call last time I did this. Let's do Lindsay. Lindsay, what's the half-life? Oh my God. Did you already answer that before I called your name? Oh my God, how funny. All right. Or I find it funny. Okay, so exactly, my half-life is 3. So now it wants to know how much is left after 20 days. How can I figure out how much is left after 20 days? Let's do somebody I didn't call last time. Isabella, how can I figure out how much is left after 20-day period? Okay. Well, all right. So tell me this. 20 days, is that a total amount or is that a time? It's a time. So what you do is you take the 20 and you substitute it in for time. I've got this little bug in here that is bugging the crap out of me. Okay, so we substitute it in for t. And then we just take this and we plug it into our calculator. Whoops, oh my God, what's going on? Raised to 20 divided by 3. And we have 0.49 grams remaining after 20 days. So this is an exponential decay. I didn't show you a little graph of this, but remember, decay means we're going down. So an exponential decay, oh gosh. An exponential decay function looks something like this. Whenever something is exponentially decaying, it actually never equals 0. Right? It gets closer and closer and closer to 0, but never actually equals it, which is really depressing when you think of like radioactive substances, right? They never actually go away. Okay. Any questions on these types of application problems? Okay. So now we're going to talk about continuous growth and decay. If you think about last class, what formula did we use to find a continuous growth for interest? What formula did we use for finance when we are continuously compounding interest? Yes, PERT, exactly. We use the exact same formula here when we're continuously growing or decaying. The principal or the initial, remember this P just means initial amount. It doesn't have to be a money, it's just the initial amount. Times E, which is not a variable, that's Euler's number, raised to the power of R times T. So now, because we are also encompassing decreasing, like you're asking, Peyton, we have to think about whether or not the rate is a positive or if it's a negative. For example, in number 6, it says the population of a town is declining at a continuous rate of 1.5%. If the current population is 16,000 people, find the population in 8 years. What this means is, I'm going to write down my principal, my initial amount, which is 16,000, write down my E, which is Euler's number, but for my rate, because I am declining, I'm not just going to put 0.015 because I'm going down, I put a negative 0.015 raised to the power of T. So anytime it tells you it's declining, you have a negative rate. So now it wants us to find the population in 8 years. All I have to do is take that time and substitute it in for T. So I have 16,000 times E, which remember we can get Euler's number by hitting second ln, negative 0.015 times 8. And you get 14190.73. However, what is wrong with just circling this answer and moving on? Okay, let me ask you this. Can you have 0.73 of a person? Right. You can't have 0.73. Now, I know that this, people think, oh, but you can, because people can have lost limbs or organs removed. No, that's not how we're referring to this. What we're referring to is 0.7 formed. So it's more relatable to like a baby growing while a woman is pregnant. It's only 0.7 of the way through the pregnancy. They're not quite formed yet all the way. So, how many people are there actually? Okay, thank you, Sniggy. Yes, we round down when referring to people. That pregnant woman hasn't given birth yet. We can't count that. We're not going to get into life debates, but we can't count that as a person, all right? So, we have 14190 people. Whenever dealing with people, or anything living, really, like animals, we round down. Any questions on this one? Okay, now we're not going to do logistic growth. It's not something we're going to deal with And we're going to move on to our exponential growth and decay applications. So what we've done up until now is just plug a number in and compute it in our calculator, right? That's all we've done is plug in a number and figure out what our total amount is given that number. Now we're actually going to have to solve for a variable. We're going to have to do a little bit of work to get our answer. Now this is why we practice. This is why we actually learned how to solve for exponential and how to solve for log. Because we're going to have to solve for variables in these application problems. So let's do this first one. Mark started a new blog to write about his travels. In its initial week, the blog had 800 readers. From this point on, the number of readers each week increased by 25%. That's awesome. Use an exponential growth model to find the week in which the number of visitors reaches 10,000 people. So apparently Mark is pretty popular. Like, this is not realistic. But we know that we're exponentially growing here. And also we know that we're trying to find the week in which his visitors reach 10,000. And it says it's increasing each and every week. Because our units for time are the same, we're not computing the increase multiple times per week. We can just use the formula that does not have an n in it. Does that make sense? Because we're starting with an increase per week and it just wants to know how many weeks it will take to reach a certain amount, we don't need to worry about computing multiple times within that period. So we don't need to worry about n. We just use this formula here. A equals the initial amount times 1 plus the rate raised to the time. So my initial amount here is 800. My rate is 0.25. And t is my time. Now, where does that 10,000 go? I have an extra number here that I have not put in my formula. Where does that 10,000 go? Yes. 10,000 is the total amount. It wants to know how long it takes to reach a total amount of 10,000. We're actually having to solve for t in this problem. We're not plugging in for time. We're not plugging in for t. Instead, we're solving for time and plugging in for the total amount. So instead of A, I'm going to write 10,000. And then I'm having to solve for t. Who knows? What would be my first step in solving for t? I'm trying to get t all by itself. That's how we solve for a variable, is we get it all by itself. What's the first step in getting that variable all by itself? Close, Kate. What operation is happening between 800 and 1.25? Is it addition? Because that's when we, right. If we had been adding between the 800 and the 1.25, then we would have subtracted. But because it's multiplication, what do we do to get the 800 off of that 1.25? What's opposite of multiplication? Yes, we divide both sides by 800. This removes the 800 from the 1.25, and I'm one step closer to getting the t by itself. So let's see. I don't know what this is off the top of my head. 12.5. Now, here comes the tricky part, and I'll be impressed if someone can answer me right off the bat, because I kind of had to lead into first period getting this correctly. What do I do to get the t by itself now? So, not quite. Remember, if something is being squared, we can square root to get rid of the square, but this isn't being squared. This is being raised to the power of t. Or in other words, this is an exponential term. Yes, Peyton. No, it's not divide either. You have to think this is, and for some reason this just doesn't stick. And it's not your fault, like it's because you haven't been exposed to exponential enough. Opposite operation of exponential is log. Anytime you're trying to undo an exponential, you have to do log. Anytime you're trying to undo a log, you have to use exponential. This is because these are opposite operations. Just like before, when we had two terms being multiplied, we had to perform the opposite operation, which was divide. You have to think, okay, if I'm trying to get something out of an exponent, a variable out of an exponent, opposite of exponential is log. So, you take the log with the same base on both sides. Now, what is our base number in this problem? What is our base number? Let's see. Let's ask somebody who I didn't ask last class. I think there's only one more. Ariel, what is our base number? Ariel going once. Ariel going twice. Okay, let's see. Matthew Harris, what is my base number in this problem right here? So we got rid of the 100. 100, oh my gosh. We got rid of the 800. Now I'm looking here on this step. What is my base number? Remember, base is the bottom of an exponent. Yes. Oh, Lauren, you answered for Matthew. I was trying to get Matthew to answer. Okay. Yes. It's okay. It's all right. He had already tried. Yes, Matthew, exactly. We need to take log of base 1.25 on both sides. Now, I know a lot of you had troubles with Math Excel not accepting ln. A workaround is to not use ln's and instead use logs of different bases like I am here. So instead, you can take log of the base on both sides. Or if you don't want to type in ln, like Math Excel isn't accepting ln, you can type in log base e. That is ln. You take log base e. Anyway, I'm going to compute this log in my calculator by pressing math and going to log base, log of 1.25 of 12.5. And I get 11.32. Is equal to t, because log of base 1.25 of 1.25 cancels, leaving you with just T. Now, it's asking how many weeks it will take to reach 10,000 people. Bye, Sniggy. What should be your answer? If someone asks you, like, oh, how many, oh no, I don't know. Man, what could you ask dealing with weeks? How many weeks? Okay, how many weeks does it take to study for the SAT? You wouldn't say, oh, it takes 11.5 weeks. You would say, about. Now, what I'm asking is, I want this rounded to a whole week, is what I'm saying. So, has this mark gotten 10,000 people at 11 weeks yet? At the 11-week mark, does he have 10,000 people? Right, Kate, yes. You would say it takes 12 weeks because at the 12-week mark, he has already received 10,000 people, 10,000 visitors. So we would say about 12 weeks. Okay. Now, number 2. I think I'm going to skip number 2 because it's pretty straightforward. The only difference is it is a continuous exponential growth model, meaning we would use PERT. Yes, that's about the only tricky part about this. And it's having us to find the rate. So we would be solving for R here. It gives us the time. It gives us the initial amount. It gives us the total amount. We would just solve for R here. So it's pretty similar to number 1. Let's go ahead though and do number 3 because it is a little different. A certain medicine has a half-life, that's our key word, of 5 hours. If a patient is given 500 milligrams at noon, at what time will they have 100 milligrams remaining in their bloodstream? Half-life means I'm going to be using my half-life function. So, I know my half-life is 5 hours. I know my initial amount is 500. And I also want to figure out at what time this person will have 100 milligrams in their system. So, where should I put that 100? Let's see here. Lauren Wilson, where should I put the 100? She's not here. Let's see. Josh Lewis, where should I put the 100? Josh Lewis going, what? Yes, exactly, Josh. Okay, you're present. 100 is the total amount remaining. So that goes over here on the left, and we're trying to solve for t again. So, what is my first step in solving for t, David? What do I do first to get t all by itself here? David. David going once. David going twice. Okay. Let's see. What about Sydney Prout? What's the first thing we do to get t by itself here? Before we log both sides. So I'm glad you said that, Sydney. Thank you. Let me mark your present. Before we can log, you are right that we are going to have to log to get the t out of the exponent. But before we can log, we need the exponential term to be completely alone on one side. Right now, it's not completely alone. This is our exponential term. We still have a 500 with it, right? Yes, Aubrey. We first need to divide by 500 to get that 500 off of our exponential term. So now what do we do to get t by itself? Let's do Abby Terry. What do we do to get the t by itself? What's our next step? Okay, if you look up here, this is the same step as right here. What did we do in this step to get the t by itself? Yes. But what about the s? The 5, you mean? It's okay. We're going to deal with that. Right now, we're just trying to get the t out of the exponent. So, and that's a 5. I know, I write my 5s so badly. So right now, we're just trying to pull it down from the exponent. So, no, it's fine. So, we're going to take log of the same base on both sides. Now, what is my base number, Josh Strickland? What is my base number, Josh Strickland? Josh going once. Josh going twice. Okay. What is my base number, Lauren Moore? Oh. Lauren Moore. What is my base number here? Close. What's above the 2? So what is this number? 1 over? Yes, yeah, that's my base. Yes. I know it's kind of written weird, yeah. But my base number in total is 1/2. Good. So, let's see, let's mark your present. So, I need to take log base 1/2 on both sides to get rid of that base number, to get the t out of the exponent. Because log base 1/2 of 1/2 cancels to 1. They're opposite operations. Leaving you with just t over 5 on the right, and let's see what's on our left. Log, I have to do math up to get to my log base. Log of 1/2, whoops, not 1/5, 1/2 of 1/5. And you get 2.32. Now, notice, the t is not by itself yet. What should I do lastly here, Samantha? What should I do to finish getting the t by itself? Samantha going once. Samantha going twice. Okay. Lane, what should I do to finish getting the T by itself here? Lane going once. Look, so this is actually not, we've seen this many, many times, okay? It's just this is a hard problem, so you're assuming this is hard. Look at this. I need to get rid of that denominator of 5, that division of 5 under the T. Yes, Lane, exactly. You got it. You just needed me to say it wasn't quite as tricky as you thought. So I multiply both sides by 5 to get rid of the denominator of 5. So I'm going to multiply this by 5. And I get 11.6. Now, if someone asks you, okay, how long does it take for something to almost all the way get out of your system, would you say, oh, it'll take 11.6 hours? What would you say? Do people, if it wanted us to round, yes, Lauren, that's what I'm looking for. We need to convert the 0.6 to a minute. Now this is how you do it when we're trying to convert to minutes. You take the decimal, which is 0.6. Now that 6 is in the what place of the decimal? What do we call that place right after the decimal? The tenths. So it is 6/10 of a decimal. Is equal, I'm on fire, is equal to how many minutes are in an hour? 60. We're trying to figure out how many minutes of our total 60 is 6/10. So, to solve for x, we just can cross multiply here. What is 6 times 60? I don't know. 360. Oh, I did know that. Oh my gosh. 6 times 6 is 36. Add a 0. Jeepers. So 10 times x is 10x equals 360. Then we divide by 10, which gives us 36 minutes. So our time, where we have only 100 milligrams remaining in our system, in our bloodstream, is what? What is our time here? Yes, 1 hour. 11 hours, 36 minutes. Or in other words, at 11:36. At 11:36 p.m. Now, the reason why it's just 11:36 is because we're starting at noon. We're starting at 0, right? From noon, we go up. If we had started at 1, if we had instead it said we started at 1 o'clock and we had gotten an answer of 11.6 and it asked at what time we would have that 100 amount remaining in our bloodstream, we would have to add 11:36 to 1 p.m., meaning our answer would have been 12:36 p.m. But lucky enough for us, it started at noon, so this is our final answer. Any questions on this problem? Okay, again, the next is logistic growth applications. We're not going to do it, but I do want to get to at least one compound interest application. So this is like more similar to what we did last class, where we're compounding more than once per time frame. So let's just do this first one. We have, if $500 is deposited into a retirement account that pays an annual interest rate of 4% compounded quarterly, how long will it take the account to reach a balance of $1,200 if there are no other deposits or withdrawals? Because it's telling us that we're compounding multiple times per year, this means we're using that formula that we used last class where we have N, a number of times per year we're compounding. Now, what is our N in this formula? What is our N if we're compounding quarterly? How many times a year are we compounding? 4. Yes. N is 4. And it wants to know at what time will our total balance reach $1,200. Meaning I'm substituting 1,200 for my total amount A. And now I'm just solving for T, just like we've been doing. I'm going to just try to do this quickly because I know we're out of time. First, we divide by 500 to get the 500 off of the exponential term. 1,200 divided by 500 is 2.4. Then I'm going to add the two terms inside of my parentheses to simplify. And I get I don't need parentheses now, but 1.01 raised to the power of 4t. I'm trying to get the t out of the exponent. So this is an exponential term. Opposite operation of exponential is log. I need to log both sides with the same base number, which is 1.01. Log base 1.01 of 1.01 cancels, leaving us with 4t. And then log of 1.01, log base 1.01 of 2.4 is 87.98. Then last step to get the t by itself is to divide both sides by 4. And t is equal to 21.996 years. And years we can just leave as a decimal. I think technically we could do like 21 years and then a certain amount of months maybe, but most cases when they want to know when it will occur and it's in years, you just put the decimal. Are there any questions on anything we've learned today? All right, remember we have a test next class, and remember to do your group quiz for extra credit.